Okay, let's get started. My, there are not many here today. Are there any questions about stuff? Yeah.
The format of the second test will be the same as the first test.
Yeah, I talked about that on Wednesday. I'm going to actually show the test without like the questions on Monday. I was going to do it today, but we kind of didn't go as far as I wanted to on Wednesday, so I don't know how far I'm going to get today. So that's why I'm going to show it on Monday. So everything that the test will cover is everything up until whatever we do today, but mostly on the stuff since the first test. And remember, it's 6 questions instead of 5, but it's 240 points out of 200 this time. So you get more bonus, and it's relatively more straightforward. Other questions? So when's the 5th problem set due? Monday. Okay. So just so you know. Any questions about that problem set? Yeah.
Are we going to go over?
No. Go ahead.
Questions 1C. Are we going to learn how to do that today?
Is that the CFG to PDA thing? Yeah. So that's what we're going to do straight away. Okay. And in that, we're going to try to do the other direction as well for PDA to CFG, but I didn't ask that one. Other questions? Okay, so what were we talking about last time? Yeah, these PDA things, and they're obviously public displays of affection, right? What are these PDA things? Push-down automata. So they're like automata. What else do we have other than just the state-based machine? Yeah, we have this little stack thing, right? And so we made this little PDA for 0 to the n, 1 to the n. And if we have a PDA that just completely ignores its stack, we just have an NFA on our hands at that point. So we showed a relation between what PDAs can recognize versus what the regular languages are. And what we wanted to convince ourselves today is that PDAs are the right model for context-free languages. So how do I show that PDAs really do recognize exactly the context-free languages? Well, what recognizes the context-free languages? The grammars, right? So how would I show that they're equivalent to the CFGs? Well, what if I convert a PDA to a CFG and an arbitrary CFG to a PDA? Is that all I need? Yeah. Okay. So like what we did for NFA, DFA. DFAs are already NFAs, but we showed how to convert an NFA to DFA. Same idea here. And the one that I mentioned was a lot easier is to convert a CFG to a PDA. And we kind of started talking about how to do that last time. So when we're trying to do this conversion, try to think about what we're converting from and what we're converting to. So we're converting from this thing that has variables, terminals, rules, and this start variable into this state-based machine with a stack. So how does a grammar actually try to generate a string? So what happens if you want to generate some particular string in a grammar? What do you start trying to do? Apply rules over and over. You start with the start variable and you apply a rule, apply a rule, apply a rule. Are CFGs inherently non-deterministic? Yeah, because there's some rule to be selected, and the way it generates it, it picks a rule if there is one to pick. So how would I get a PDA with this stack thing to emulate what this grammar is actually doing? So remember, the grammar is applying these rules and it's generating a string. The CFG does not have an input. So if you have a string in mind, you try to generate that string, but you're not given that string necessarily. It's just giving you the rules that you can apply to generate that string if you want to generate that one. The PDA, on the other hand, has an input that you have to be able to read through the entire input, and you got to work with the stack and end with a final state, of course. So what was our big idea in order to get that to work? Well, what we could try to do is the CFG is doing a derivation of that string, an application of rules over and over. Why not try to put that derivation onto the stack, and then maybe we can work with the stack and the input of the PDA in such a way that hopefully we can get the entire string, the input that we have, and have nothing on the stack so there's no rules left to apply. So that's the basic idea. So let's actually look at the grammar for 0 to the n, 1 to the n. So remember the grammar for 0 to the n, 1 to the n, which was this. Okay, let's just say that the PDA that's going to try to simulate this CFG is going to get the input 0, 1, for instance. So this is the PDA's input. The CFG does not have an input. So let's see, what does every single derivation ever start with? Start variable, right. So if I'm going to be putting this derivation on the stack, I got to be able to put the derivation on the stack. So let's put the start variable on the stack, namely the only variable in this case. Let's see, if I want to generate that string using the grammar, what rule application would I use? The 0s1 rule. So below I'm going to put the actual derivation. So this is the derivation I have. But remember, the PDA has this input it has to match, right? So if we're going to be trying to match things on the stack, which of these two characters should I read first off the stack? The 0, right? The 0's got to appear on the stack at the top, because if I'm going to be matching those off the input, I better see the 0 first. Well, what are we going to do in the general case? Well, if I see a terminal on the top of the stack, like I've applied this rule, let's say, s goes to 0, s1. Is that 0 ever going to change? No, because it's a context-free grammar. If I had a grammar that said, oh, you can replace this 0s with something else, could I say the same thing here? No, but we have a context-free grammar, so I know that 0 will never change. Okay? So that means that I can match that 0 with the input that I have. So I want to see the 0 on top of the stack so I can match with it. But that must mean I need to put the rest of the derivation on the stack as well. Well, what's the rest of the derivation so far? The s and 1. So those have to appear below. There's actually a subtle thing we need to handle, but we'll get there. So what are we going to do? We're going to read, so we see a terminal now on top of the stack, and we see the same terminal on the input. We're going to read off of the input and pop that particular terminal off the stack. So I see a 0 on top. I'm going to just pop it off the stack and read it off of the input. Oh, so what's on top of the stack right now? The variable, s. What do you think I should do with a variable? Apply a rule. Okay, well in this case, what rule should I apply? The epsilon. Well, in that case, oh, I should do it down here. So the rule application here is change s to empty. So the derivation still has 0, 1 there. But on the stack's point of view, the s effectively is killed off, and I have a 1 left on the stack. Oh, I have a terminal on top of the stack, and I have something on the input. So what do I do next? match them up, just like we did with the 0. So I cross off the 1 and cross off the 1. Oh, so now what do we know about the stack at this point? It's empty. Well, how do I check that? I need to put that special character at the beginning, right? Because I have no way of checking whether a stack is empty. So at the very beginning, I'm going to put a special character, $, whatever you like, that's not any other character, and we're going to persist it through here. So when we pop that 1 off, we see a $sign there. And so if we pop that $sign off, that tells us now we have an empty stack. So what should I do with the PDA at that point? If I have an empty stack, what do I hope to try to do? I try to accept. I may not have all of the input read. So if I go to a final state and I don't have all the input read, is that okay? Well, will I accept the input? No, but should I accept the input in that case? No, because the PDA is going to be non-deterministic. So if there is a sequence of rules to apply that make it accept, it will have picked the right one. So if it goes to a final state and it happens to not accept because it just happens to not read everything, then we know that the CFG could not have generated the string. So therefore the PDA shouldn't accept it either. Okay, so in fact, could we make a PDA out of this just by looking at this computation? But the key question is how? So let's just simulate at the very beginning. What do we do at the very beginning before I've ever done any rule applications? I push a $sign on, and then what do I push? The start variable, the grammar, which is S in here. So in fact, we can make a grammar, a PDA starting from this. So when I push that $sign on, I'm not going to read anything because the only reading that I'm ever going to do is when I see a terminal on top of the stack, and that's not the case, so I'm not reading anything here. I better not pop anything because the stack is empty, so I'm just going to push $. And exactly the same logic applies for the next transition, but for the start variable. So I'm going to fix this. Okay. Okay. So why do you think I called that state after I pushed the start variable on Q loop? I mean, it's obviously an arbitrary name, but is there a reason why I put that on? I called it that? So it's going to have some kind of loops of some kind. And what do I mean by that? So in this state, we're going to do one of two checks. If we see a terminal on the stack, what should we do? Pop it off the stack, and what with the input? Read it at the same time, match it up with the input. What if I happen to see a variable on the stack? Apply any of the rules that that variable has with it. So what are the terminals in this grammar? Let's just handle the terminals first. 0 and 1. So how many transitions am I going to have here? 2. Well, 1 for each of them. So in fact, I'm going to have a self loop here. So if I see a 0, I better pop a 0 because I got to match it up with the input. So if I see a 0, match with the 0, and I better not push anything because I want to get lower on the stack, lower on the derivation so far. So push nothing, and exactly the same thing for the 1 case. Okay, so far so good. How many rules does this grammar have? 2, right? It has this 0s1 rule and the epsilon rule. So let's look at this right here, where I pushed on the 0s1, right? How many transitions did it take to accomplish that? Well, I started with S at the beginning, Did I get rid of that first S at the beginning? Yes, I did. Well, how did I get from S to 1 over there? So if I see a variable on the stack, I'm going to pop it off, so I now know what the variable is, and I'm going to push the right-hand side of that rule on, which in this case is 0 less 1. What order should I push that right-hand side on? The 0 less 1. The 1 first, right? I can't push the 0 first because it'll appear below the top of the stack. And I want it on top because it's going to match the input left to right, just like the derivation is left to right. Okay, so I gotta pop S off, then push on a 1, push on S, then push on 0. So that, we're gonna do it in 4 transitions. You can do it in 3. So let's do it in this. So I'm not going to label the states names because it's pointless. But on these transitions, I'm not going to read because the reading transitions only happen when I'm matching up with the terminals on top of the stack. So I'm not reading here, but I got to pop off that variable. So in this case, which is S, and I'm not going to push on anything here. I could push on one of the things on the rule, but I'm not going to on this transition because I'm going to be forced to push on other things if I take this transition anyway. So remind me, which of those 3 things do I need to push first? The 1, because I need the 0 on top. So we're going to push on a 1, so that means I don't read and I don't pop on any of these other transitions. Epsilon, epsilon, push a 1. Then I do the same thing, I push on S, and then I return to Q loop by pushing on a 0. So all this really is simulating a rule application on the stack. So if I happen to take this transition, the only way I could have is if the variable S was on the stack. And what would happen is, in order to get back to Q loop, I need to push on a 1, then S, then 0 in that order. And so then I just applied a rule on the stack. And then since the 0 is on top of the stack now, then I must be able to match it up with the input and then carry on computation from there. Okay, well, what about, so we handled that one rule. What about the other rule? What should I do on that case? So I still have to, so look at this. So yeah, so in fact from here to here, I applied 2 steps at once and I probably shouldn't have. What happened here? So I popped the 0 off, so the S is now on top of the stack. Which rule did I apply in the original part? The S to empty. Well, what does that involve in terms of the stack? Well, I always pop the variable that I see on top of the stack off. I always do that. But what do I do after that? I don't do anything with the stack. So in fact, we'll have one of those triple epsilon transitions again. You could make this a self loop because it really only does one thing, but I'm going to do it in 2 transitions to make it more precise. So, more clear, I mean. So I gotta pop the S off, just like before, and then I gotta return to Q loop because I'm not doing anything else with the stack other than just popping that one variable. So I just return with a triple epsilon. Okay, so let's just recap. We're almost there, but it's worth noting what we're doing. So people walking up by don't really understand what's going on, right? It's just gibberish up there. But what are we doing here? We're pushing on this special character to denote when we will have an empty stack, Then we got to push on the start variable because we want to simulate the derivation of the grammar on the stack. And the only way a derivation can start is with the start variable, so I got to put that one on. And then we start applying rules on the grammar, on the stack of the PDA. Then if ever a terminal appears on the stack, then that must mean that in the derivation of the grammar, that terminal will never change because it's a context-free grammar. So in fact, if a terminal on top of the stack, I match it up with the input, and then I keep going. If I see another variable at any point, I just take it off the stack, and I apply any one of the rules corresponding to it. Okay, well, let's just assume we carry through this computation, and we matched up the input, and the stack is completely almost empty. What's on top of the stack now? The dollar sign, hopefully. Maybe there's stuff left on the stack, but if we're lucky, then the dollar sign's on top of the stack. So how do I check if there's a dollar sign on the stack? Just pop it off, right? So I gotta leave this state because at this point, I don't want to apply any more rules of the derivation because I'm assuming the derivation's over at this point. So that must mean that I'm not reading anything here. I am popping the dollar sign off, and I can do whatever with with respect to pushing. I'm not going to push anything here. But I must be able to go to some final state because here, if I've matched the input up correctly, and the stack is empty other than the dollar sign, then I should be able to go over there and say accept. So let's actually trace through the computation here for 0, 1, like in the grammar we did before. So I start in Q0, empty stack. I push on a dollar sign, there's only a dollar sign on. I push on S, then there's a dollar sign S on the stack. Then I can't apply any of the rule, any transition from Q loop other than the two that come out for popping S off because the self loops are for reading and popping a terminal, but there's no terminal on the stack yet. And I can't apply dollar sign because the dollar sign's not on top. So I have to apply one of the ones that corresponds to S. Well, since it's a non-deterministic machine, it will pick the one that pushes on the 0S1 thing. So it pops S off, so only dollar sign on right now. Then it pushes on 1S0 on the stack. So maybe instead of hand waving, let's do it like this. So at this point, when I've applied one rule, the stack looks like this. Okay, so that's the stack at that point. Well, I see there's only one transition I can apply because it's the only one that has a popping a 0 off the stack. And the only way I can do that is consuming a 0 off the input. So I'm not going to simulate the input because you know what the input is. So I'm going to pop the 0 off. Then I see there's an S on top of the stack. So how many transitions can I apply if I see an S on the stack? 2, because there are 2 roles. So since this is a non-deterministic machine, it will pick the other one where it just takes S off. So I go take S off and come back. So that means I just take S off. Oops. Should be a 1 here in the dollar sign. Then I see there's only one transition I could ever take with a 1 on the stack, which means I read it off the input. So that means that there's only a dollar sign on the stack. And there's only one transition now with that involves a dollar sign on the stack. And that means I pop that off and have an empty stack. And at that point, I've read the input, and it doesn't matter that the stack is empty, but that implies that I've matched everything on the stack correctly. What if instead I had like an extra S on the stack, or something like that, and I had an S at the very end when I went to the final state? Could I go to the final state? Well, if I'm in Q loop with that stack configuration, could I go to the final state? No, because the only way I can go there is if I see a $sign on the stack, but I see the variable on the stack. So there's no way I can go to the final state. So that must mean I need to apply another rule application. Okay? So the only way I can go over there is if there's nothing on the stack but the $sign, because I never push it on any other time. Okay? Any questions on how I converted this? Yeah.
Is the epsilon to the left of the comma for the input? So if you see a 1 or 0 on the input comma, then
Which transition are you referring to?
any of them, really, like the epsilon comma.
Yeah, it's just like an NFA. It just means that you can take this transition, and if you do, you're not going to read anything off the input. So like from Q0 to Q1, I'm not reading anything off the input. It's just the input head, it doesn't move where the input is.
But with the loop, we have a 0.
Yeah, then it must progress. Yeah.
Input string.
Right. And the only way that it could move ahead on the input string is if I see the same character off the input. Off the stack. So it matches whenever I see a terminal on the stack itself. Okay? Yeah.
So if there's like an extra S left over as you circle there, what's stopping the machine from going on the pop-off S?
It probably will in this case, yeah. But that means there must be some other rule application it must do, because it can't go to a final state otherwise.
Okay.
There's a question over here, I think.
I had the same.
Okay. Yeah. Any other questions about this? Yeah.
Can you then generalize this?
Yes. So what do you do? So in general, let's see if I can remember how to do it. So I'm just going to write it in an informal way because it mirrors the one we did above almost exactly. So we're going to push $sign on first, always. Then we're going to push the start variable, always. I should rename that to Q loop to match. Then at the very end, I will always go to a final state, QF, let's call it, and I pop $sign on when I go to the final state. So the base structure is exactly the same for every single grammar when you convert it to a PDA. Well, if we mirror what we did above, then we're going to have a self loop on Q loop, which involves some terminal A, and you pop that same terminal A and push nothing for all terminals A. So it's just exactly the same as the grammar up here, but for every terminal you have one of these self loops. And then otherwise, we're going to have a set of transitions that goes out and comes back, where we first pop the left-hand side variable, and then push the right-hand side of rule in reverse order, because we want the left part of the rule, the right-hand side of the rule, to appear on top of the stack. So if we look back at the 0s1, 1, we push the right-hand side of that rule first and then progressed left. So we pushed it in reverse order. Okay, so but this works in general. So why does this work in general? Well, any derivation must start with the start variable. So we put that on. Then if we look at a derivation in the arbitrary grammar, then it's some sequence of rule applications. Well, and let's just say it produces some string W. So for the PDA to have input W, what happens is the PDA, what it's going to do is it's going to apply the same rules using the stack. And when a terminal is ever produced in the derivation, it matches up with the input via the self-loop transitions. But then if a variable ever appears, then we apply another rule, just like how the grammar did. But keep in mind this. Could a grammar apply things not necessarily in leftmost, as a leftmost derivation? Could it do some other variable than another variable not necessarily leftmost? Could a grammar do that? Yeah, certainly. But is there always a leftmost derivation? Yes. So that's the key here. Note, if I have a stack which has some variable up here and then some place later has another variable, etc., then if the derivation I'm looking at is not a leftmost derivation, I could want to do something with that lower variable. But since there's always a leftmost derivation, then the PDA, what it's going to do is going to do the leftmost derivation. Okay, so if there's not always a leftmost derivation, I can't guarantee this. But since there always is, then we can. So the PDA is always going to do a leftmost derivation of the string that it gets. Okay, any questions about this in the general case? Cool, so what we just showed is that, as a theorem, that every CFL can be recognized by a PDA. Nice. Because we can convert any CFG into a PDA. Sweet. Are we done? Oh, what do we have to show? Ah, the other way. We got to be able to convert a PDA into a CFG. So again, think about what we're going to try to do. We have this thing with states and a stack and final states and all that, and we want to convert it to something that has variables and terminals and rules and all of that. Question for you. Does my PDA always look like that particular pattern? Because if it did, then we could just extract it from the PDA and then we'd be all set. Does the PDA always have that form? In fact, the first transition may pop, which would be a dumb PDA, but we can't assume anything about the PDA necessarily. So remember, what the PDA did to simulate the CFG was to simulate the derivation on the stack. But now we got to try to have the CFG simulate the PDA. Okay? That seems quite hard. So let's try to figure out, maybe we could take our general PDA model and maybe make it easier to work with. So what should the CFG try to simulate? Well, let's see. What could it try to simulate? Well, it could try to simulate the things that are read on the transitions, but it could easily do that for an NFA. So what should it try to simulate instead of the PDA? Starts with this S and ends with a TAC. Stack. Oh, okay. Well, there are some potential problems that might happen. Well, could a PDA push and pop simultaneously on the same transition? Yeah, that's allowed in a PDA if you look at the definition. So if I have whatever below and then I have an A on top, I can instantaneously in one transition convert that to some other character if I wanted to. Could I also have a transition that neither pushes nor pops? Yeah. So if I'm going to try to simulate the stack, if I see something like this, that might be hard for the context-free grammar to work with. But if instead I insist that every transition either change the stack in one way or another by increasing in height of the stack or decrease in height, never stay the same, could a grammar take a note of when that happened? Yeah, because it can see, oh, that's the thing that changed. And since, if you think of a CFG in terms of when you apply a rule application as going down a layer, like the one in your assignment, you're going down a layer, then if I have something like this, if I can assume I can make that bit, then I can make that top terminal. Okay? So our first goal, so this is a multi-step goal, but the first goal is, can we ensure every transition of a PDA, a PDA, either pushes or pops, but not neither nor both. Well, let's soak it in for a second, then we'll get to that. I know triple negative right there, but could we actually do that? Well, if we had a transition that actually does do exactly one of push or pop, so it either pops and doesn't push, or it pushes but does not pop, are those transitions okay for this to work? Yeah, those are okay. Well, the two cases we need to worry about are the ones that may read or may not read, and doesn't do either push or pop. And then the other case is when it does both. Right, those are the two cases that don't fit into this part. So how do I handle those? Say the one that doesn't do either. Well, what could we do? Could we simulate this transition with some transitions that do exactly one of push or pop? Yeah, what could I do in this case? Yeah. So let's see. Let's handle the second one as you said. So let's have 3 states instead of 2. Well, one of them has to read that A, although A may not be a character. So let's say that we read on the first transition. It actually doesn't matter. But I have to pop first. Why do I have to pop first? Because if I push first, then the thing I want to pop is not on the top anymore of the stack. So I need to pop first. What am I popping in this second transition? The X, right. So X, I'm not going to push anything because I want this transition to do one of the two. And the other transition is going to always be no read. It's going to be no pop, but it's going to push the thing I wanted to push. Cool. So I can convert any transition of the PDA that does both into 2 that does one of the 2. So this one's actually analogous. What about the one that does neither? Right, the push something on, then pop the same thing? Yes, it has to be the same thing. So it can be an arbitrary character. So I'm going to separate those. So it's always going to be A and epsilon, just like before. This one, we're going to push, let's say, an X. It could be anything you like. Then pop X on the second transition. Okay? Any questions why we can do that? There's actually a very good reason, other than the motivation for why a CFG can do it, for why we want to have it be like this. But let's see. suppose we knew this. So let's see. Let's suppose we have a start state here. So this is just a hypothetical. The PDA might not look like this, but let's just assume that we have something that looks like this. And let's say that we know how to get from Q0 to this second state, Qi, this state in the middle. Let's say we knew all the strings that took me from Q0 to Qi with the same stack height. So Q0 starts off with an empty stack, and Qi, let's hope all the strings that we want to consider end in an empty stack. So look at all the strings that end in Qi with the same stack that we started with, exactly the same. Okay, and then let's suppose we knew all those strings that take me to some final state. Let's just say let's just look at some final state. There may be more than one final state, and we'll handle that in a bit. Let's say we knew all the strings that took me from Qi to Qf with the exact same stack height, no change in stack height. Do I know all the strings that take me from Q0 to Qf with the same stack height? If I know all the ones that get me to the middle and from the middle to the end? There may be other ones, but do I know some at least? Yeah, it's just whatever string takes me from Q0 to Qi, and then concatenated with whatever string takes me from Qi to Qf. Okay, let's see. But I may need to handle this for more than one final state, right? Because a PDA may have more than one final state, other than the PDA up here that we guaranteed only had one. But can we guarantee there's a PDA with exactly one final state? Can we convert any PDA into one that has exactly one final state? Yeah, how do we do that? Oh, yeah, so we can actually, so this is the second step. So every PDA can be converted into one with exactly one final state. And in fact, the proof is almost exactly the same as for NFAs. So just take an arbitrary PDA like this. Let's say it has two final states, for instance. Then what we do is we blank those states out, those originally final states, make a new final state, and triple epsilon our way over. For an NFA, we have a single epsilon, but here we need 3 because of push and pop. Okay, well that's no issue. But didn't we just introduce an issue with these new transitions that we tried to fix earlier? Yeah. Well, could I fix those? Yeah. We already showed how to do that. So let's just assume we fixed all those transitions. Let's go back to the same argument we had here, where I looked at all the strings that took me from one state to another with the same stack height. Does a PDA have to end with this stack empty? No, the only requirements, remember, are that it reads the entire input and of course ends in a final state. It doesn't have to end with the stack empty. But could we ensure that there is some way for it to end empty? Yeah, what could we do with our picture right here to ensure that there's some way that the PDA could end its stack empty? Well, what we could do is go over to the final state and just pop every character off. Couldn't I do that? Yeah, so let's actually do that in a different color. So here, I'm going to not read pop and obviously not push for all A in the stack alphabet. So if I have any character at all, I don't have to take this transition, but I'm allowed to if I want to. And the good thing about this transition is it satisfies exactly one of push or pop, so I don't have to fix these transitions either. Nice. So let's see. We can assume now that our PDA has exactly one final state, and every transition either pushes and doesn't pop, or pops but doesn't push. And we ensured that if a PDA can accept this string, with the stack empty or not, there's another way the PDA could accept with the stack empty if it wants to empty the stack. Okay? So now we're ready to discuss the main idea, then we'll get into details. So again, what is the CFG trying to simulate of the PDA? The stack. Okay, so let's actually look at the stack. Let's look at a computation and let's see what happened with the stack. So let's see. So what I'm going to plot here is the horizontal axis is going to be time, namely transition after transition, what happens. And the vertical axis is going to be the stack height. So I'm not going to keep track necessarily because we don't have to in this case, as we'll see. I'm not going to keep track of the contents of the stack, but all I'm going to look at is what happened to the stack height over time. So at the very beginning, what's the stack height? 0, right. So down here, the stack height is in fact 0. It's a no-brainer there. What happened on the first transition? It must have went up. Could it stay flat, the stack height? No, because we ensured that the PDA always either pushes and doesn't pop or pops but doesn't push. So in fact, the stack height either always increases by 1 or it decreases by 1 on every transition. Okay? That'll actually be very key. So let's see that first transition. It pushed, so it went up to here. And then maybe it went back down to 0, I don't know. This is just an arbitrary computation, but let's just assume that the stack height looks like this. Maybe it touches back down at 0 one time, then it comes back up and it does all this. And then let's say it enters the final state with a non-empty stack. Question, could the PDA, when it accepts, have an empty stack? Like try to get an empty stack? Yeah, because we have those popping transitions. So in fact, I can assume that the PDA will end with an empty stack. Yeah.
Couldn't it be like a language that's description was turned string 011 into string 111 or something like that, and then the final state would necessarily have some type of, like it would have to have something there, like you couldn't just get rid of all of it?
I don't know what you mean by turn the input 011 into 111.
I'm just trying to think of like some computation that doesn't, like it leaves with like something, like almost like a return value or something like that.
So there's a modification of DFAs called Mealy and Moore machines that output, when they take a transition, they like literally output a character.
Okay.
And then you can talk about the languages that Mealy and Moore machines output. I'm not sure if there's I'm sure there's a variant for PDAs, but of course the PDA doesn't output anything other than it accepts or not.
Okay.
But yeah, I'll look that up, I'm not sure. Other questions? Okay, let's see. Let's say that, I'm going to delete the word time here, but let's say that the input is whatever it is, but let's say that this part right here, on all the transitions, whatever we did, we read the input, we read the string x. Let's call it x1 actually. And whatever we read from this middle point over here to all the way to the end, we call x2. What's the entire input to the PDA? Oh, it's just x1 concatenated with x2, because those are the things I read on the first half, things I read on the second half. So let's see. If I know how to get from state qi, and the state in the middle is QJ with the same stack height, and the last state is QF, let's say, then I know all the strings by induction that take me from QI, or it's Q0 in this case actually, to the single final state. How many start variables can a grammar have? One. So what is the language of the PDA in this case? All the strings that take me from Q0 to QF. Could I model that as a variable? All the strings that take me from one state to another state, and for every pair of states. And then I just set the start variable to be all the strings that take me from Q0 to QF. So why did we have one final state instead of arbitrarily many final states? Because if I model it that way, I have all the strings that take me from this start state to this one final state. There's no other place to accept. So that's why I have exactly one final state. Okay, so the way that we're going to model the grammar here is we're going to call it A sub PQ. So A sub PQ is a variable. And what we want this variable to represent is, so I'm going to put it in quotes because I haven't shown this yet, but this is what we want it to mean. All the strings taking the PDA from state P to state Q with, I should say, empty stack to empty stack. i.e., it's exactly the same stack it was before. So that's what we will want this variable to mean. Okay? Well, if I look at the variable A sub the start state of the PDA and the single final state of the PDA, isn't that what we want the language of the PDA to mean? That take me from this one state, this start state, to this single final state. That's the language of the PDA. Because at the end, when I get to QF, I can't read anything else anyway. So I'm going to actually set this to be the start variable. Question for you. If I do this PDA manipulation and I end up with 10 states in the PDA, how many variables am I going to make? Well, how many choices do I have for P? I have 10, right? Any one of the states to any of the other states. How many choices for Q? 10, right? Because I have 10 states. So how many choices in total? Don't say 20. 100. Because it's any state to any other state. And then what we'll do is we'll relate these variables together so that we can actually build the entire grammar from that. Okay, but are there any questions before we move on? Yeah.
So why is the same height necessary?
Oh.
I mean, PDA might never be of the same height. The stack might never be at the same height. Is it possible?
We guarantee that's a possibility because we ensured that the stack will eventually go all the way down to 0. But, or there is a way for it to go down to 0. You're right. It could, in general, go straight up and then straight down. That is definitely possible. But I'm just looking at it in the general case. But you're completely right. Other questions? Yeah.
Well, I don't understand why it's difficult for a grammar to understand when the height is the same. That is, why are we ensuring that we either push or forward?
We're going to get to exactly that, and it's really cool. It's a very clever idea, but we'll get there in a second. But any other questions? Okay, so now let's start figuring out for special cases, what strings can I make for certain variables of this type? Well, let's look at one particular case. So this is called type 1. Well, let's look at A sub P, P. So the same state in both, so all the strings that take me from state P to the same state with the same stack. Okay, let's look at that particular case. Well, of course, I may have some roundabout way that reads a long string that pushes on a whole bunch of things and then pops a whole bunch of things and eventually returns to the same state. Of course, that can happen. But what is one string I guarantee this thing can make? Empty string, right? Because if I don't take any transitions at all, what string have I read so far? None. So I'm still in the same state. I haven't moved anywhere. So therefore, one thing that this can make is empty. It could certainly make more, and in fact it will, in general. But one string it can make is empty. Cool. Let's see. What about this situation up here? But instead of Qi, Qj, and Qf, I have, let's say, P, R in the middle, and Q over here. Can you relate P, R, and Q together? Oh, let's see. If I want to solve the problem A, P, Q, go all the way over here, and I have this middle point in the middle, how can I relate going from one part to another? Oh, yeah, it's APR. So I'm not a tax lawyer or anything. No APR. And then ARQ. Right, it's just looking at the picture. And the question that was raised earlier, it could definitely not touch 0 at some point. That's definitely fine. But I want to account for that possibility if there is one. Okay, so if there is that possibility, I just want to account for it. But do I know what these three states are? The P might not be at the beginning. If I take a cross section of this picture, then I did a bad drawing. Let's look at this one. Let's look at these three instead. Well, that could be a candidate here as well, because it's the same empty stack relatively to the other two parts. So, do I know what those three states are in general? Is it wrong if I include every possibility? No, because if the PDA could have done it, I might as well account for that possibility anyway. They may be completely nonsensical to do it this way. But if I include every possibility, there's never a wrong thing with that. Same thing as like for the NFA to DFA conversion. There may be a lot of states I might not need, but I'm just going to include them anyway, just in case. And for formality reasons. So this is for all P, Q, all triplets of states in the PDA. So the key to note here is, for this rule, the ends of the right-hand side match the variable on the left side, and the two inner parts on the right side are the same. So that's all that we insist here. Any questions on why that's true? If we just left the grammar like this, like I didn't do anything, just these, I should also say, this is type 2, my bad. So there's going to be a third type. But if I just left it at type 1 and type 2, what would be the language of the grammar? Could it ever generate anything of terminals? No, because it's just either empty or just two variables, but that's not going to help me. So when we get back from break, we're going to talk about how to incorporate this idea of changing stack heights and reading things at the same time to finally complete the CFG we're after. So let's take a break.